Welcome to Cosplay Engineering. I'm ACraftyHobbit, and this month the focus has been adding single LEDs to your cosplay and programming them for various effects. In this episode, I will be talking about RGB or programmable LEDs. There are different kinds of these LEDs. I will be focused on an RGB anode and a driver chip LED like a NeoPixel, Dot Star, and Pixie. I will be demoing with a Pixie for this episode. As always, I will teach you how to wire up the electronics, break down the code to program various effects, and finally assemble it all together into actual props. Let's get started. For my RGB anode, I designed a Navi from Zelda. I broke it into 3 pieces so that I'd continue to have access to my electronics. The majority of my electronics will be housed in the base of the Navi design, with a hole for the button. The top and wing pieces easily snap onto that bottom to create the whole look. For my Pixie, I designed the Up-N-Atomizer from GTA. I had a lot more flexibility since it's bigger on where I could put the electronics. I settled on the battery in the handle and the microcontroller in the chamber with space for the wires to run between the two. The light is held at the bottom of the barrel to light up the disc. The trigger is designed to move, so when it is pressed, so is the button. Now on to wiring. Like usual, I start with my Ardiuno Uno and a breadboard. I'm going to start by wiring up the RGB anode first. Unlike the colored LED, this one has 4 legs. The longest leg is wired to power. The other 3 legs control the light's color. The single leg next to the longest leg is red. After that, power leg is green, and finally blue is on the outside. Each leg will need a 220 resistor to it and a wire back to pins on the microcontroller. Each leg gets its own pin. Red is pin number 11, green pin 10, and blue pin 9. My button is the same wiring as with the colored LED. It needs power to it, a 10K resistor to ground, and a wire back to a pin on the microcontroller. I'm still using pin number 2 for my button. Here's the final wiring diagram. Moving on to the Pixie. This is actually a tiny version of what I just wired, but because these LEDs are integrated alongside a driver chip, they can be controlled through a single data wire versus 3. However, because of that driver, they cannot light up on their own like the anode. These LEDs do require a microcontroller and some programming. To wire them up, I run a wire to the power pin, back to power, a wire from the ground pin to ground, and a wire from the data pin to pin number 6 on the microcontroller. Now that the wiring is done, let's move on to code. I took the code from my on and off example from my colored LED video and changed it to work with the RGB anode. At the top this time with the button pin, you'll see 3 constant variables for the LED. Each one matches the pins on the microcontroller to the correct colored leg of the LED. Next, the same variables from the original sketch. The setup function to initialize the connection now to all 3 pins, the button, and the microcontroller. Next, the loop function. For the colored LED, I was setting a LED state from low to high depending on mode. This time, however, I changed the code in each mode. I had mentioned previously this part was interchangeable. Functions can actually be called inside the loop. That is what's happening with this particular code example. When the loop is run, it calls the function setColor. setColor takes in 3 values, the red value, the blue value, and the green value. When working with RGB anode, the low and high values are reversed. So 255 is actually off and 0 is on. This is hard to keep track of in my head, so I have the function do the math for me. It then analog writes those values to the pins of the different leg. So this time when mode is equal to 1, it calls the set color function and provides the values 0, 255, 255, which makes the light turn on and be aqua. When mode is equal to 0, it calls the set function and sends 0, 0, 0. This means the light will be off. Now I'm going to make it so that every time the button is pressed, it changes the light to a new color. There are many different ways to write code. In this next example, I am still using mode, but I've simplified the code so I don't have to keep writing if mode is equal to. The same constant variables are still there at the top, followed by the variables to track the button states and mode. Next is still the standard setup function that initializes the connection. The loop is where things have changed. This time, when the button is red, it compares states and uses a delay to account for the debounce. Once it confirms that the button was pressed, increase the mode. If the mode is greater than 6, return to 0. Switch case statements are a substitute for long if statements that compare a variable to several integer values. So for this, it's looking at mode. If mode is equal to the value of the case, do that action. In this situation, each mode will write a different color to the light using the set color function. Moving into the pixie. When using Adafruit lights like the NeoPixel, Dot Stars, or Pixie, you need to download the libraries in order for them to work. These libraries provide examples to test the wiring. Those examples are a good place to start to know what needs to be included in your sketch in order to get the light to work. This is a strand test for the pixie. At the top of the sketch, you'll see Include. This calls all the libraries for the pixie and allows access to all the functions within that library. Define here is defining the pin for the pixie and letting the microcontroller know how many pixies we are using. In this case, we are only using 1. This is very similar to our constant variables in the previous sketches. In the setup this time, the connection is still being initialized, but it's also just testing the light by setting the lights to red, green, and blue. Into the loop. The Adafruit is using 2 functions here. Wheel, which is generating the entire color wheel, and rainbow cycle, which is calling that wheel to then generate those colors into the pixie. Rather than dive into too many details, let's simplify the code and use it to beam a rainbow whenever the button is held. From the strand test, I kept the following: the include for the libraries, the define for the pixie pin and num pixies. I also added an additional define for the button pin. These sections help establish a connection to the pixie, and I kept them from the strand test as well. I also created 2 additional variables: button state to track when the button is pushed, and current color to track the current color of the light. This is the simplified setup function that still initializes that connection between the pixie, the button, and the microcontroller. Pixies are 3-watt LEDs. This line, strip.brightness, controls how bright that light is. You want to adjust this number so you don't blind yourself or others. In the strand test, it was set to 200. I lowered it down to 50 when testing my code. This loop is set up just like the other button sketches from the colored LED. It first reads the button. If the button is pressed or high, for each pixie, set the light to a particular color on the color wheel. Increment that color so that it transitions to the next color on the color wheel. If it has reached 255, return it to 0. If the button is released, turn off the light. With the different effects programmed, it is time to move from the breadboard to soldering it all together. This time I started with the microcontroller. I attached a wire into VIN, which will provide power from the battery to the board, and 2 wires into ground, one for the battery and the other for the button. I attached 2 wires into the 5-volt pin, which will provide power to the button and the anode. I soldered a wire into pin number 2 for the button. For the anode, to keep track of which leg is what color, I soldered a blue wire into pin number 9, a green wire into pin number 10, and a purple wire into pin number 11. I attached a 220 resistor to each of these wires on 9, 10, and 11. I then moved on to the button. I attached a wire and divided it in half. One of those halves gets the 10K resistor, which is attached to ground. The other half goes to the wire connected to pin number 2. Moving on to the anode, I attached the wire to each leg, again matching the colors. Those wires are then connected to the resistor on the microcontroller to the correct pins. I plug it all in, making sure that it is working correctly. Here is a diagram of it all soldered together. Moving into soldering the pixie. Just like with the anode, I attach a wire to both ground and VIN for my battery. Because the pixies are 3 watt, they are more expensive than other single LEDs. So I decided to use a male-female connection wire instead of fully soldering the pixie to the board. That way I can still use the light on other projects. The red wire is soldered to the 5-volt, the white is soldered to ground, and the green is soldered to pin number 6. Don't forget, you're also going to need another wire from both ground and 5-volt for the button. Next, I soldered the female wire to the pixie. The red goes to the positive hole, the white goes to the negative hole, and the green goes to the data in hole. The positive and negative holes are very large on the pixie, so I had to first solder them to thicker wire before I could attach them to the actual light. Next, moving on to the button. I attached the power wire to the button, then I solder a wire onto the opposite side of the button. This will be divided in half, and one will go to pin number 2 wire and the other is to a 10K resistor to ground. Here is the final soldering diagram for the pixie. Here's a couple notes about the electronics I used. NeoPixels, dot stars, and pixies are great, but if you're on a budget, you might want to consider using an anode. While they require a bit more wiring, they are the cheapest color-changing LED. My microcontrollers for these projects were Arduino Nanos. If you get the knockoff ones from China with the ATmega 328P chip, make sure you are using the old bootloader in order to upload sketches to them. They won't work otherwise. Unlike the trinket used in my colored LED video, which could be powered by a 3-volt lithium-ion battery, the Nanos need 9 to 12-volt battery in order to power them. If you're hurting for space, a 12-volt is the way to go. Color-changing props are always a fun addition to your cosplay. Thanks for watching this episode of Cosplay Engineering. Next month, I will be moving away from single LEDs and into series LEDs, aka Christmas lights. To see what I'm up to between episodes, make sure to follow me on my social media. Likes are always appreciated, and make sure that you're subscribed to this channel and hit that bell. Stay safe out there, wash your hands, bye!